Today we're going to look at Dijkstra's shortest path algorithm. Edgar Dijkstra was an influential computer scientist working from the late 50s to the 80s, and amongst his students were Tony Hoare and Nicholas Wirth. Wirth and Hoare created the Pascal programming language. Let's imagine we want to find the least cost route across this graph from A to J. That means we need to find the sequence of nodes we must visit to get from A to J at the lowest possible cost. That is the objective of the algorithm. So just to reinforce that, our objective is to find the sequence of nodes we must visit to get from A to J at the lowest possible cost. At first look, Dijkstra's algorithm is a little bit complicated. However, if we work through the steps involved, all will become clear. Looking again at the graph, we will start our algorithm at node A. We're going to need a table to keep note of the steps we take, so let's add that now. The table will list the nodes along with the shortest distance from node A to each node, as well as the previous node that led us to that node. We'll need the previous nodes when we work out our finished route at the end of the process. We mark the A node to show that it's the current node. Node A is linked to nodes B and C, so the next thing to do is to replace the infinity distance with the values from the graph, in this case 50 and 25. The infinity distance is crossed out to show that it's no longer relevant. We also write the current node into the previous node's field, so we know how that node was reached. We now mark the A node as visited, denoted by a V. Now comes the key part of the algorithm. We look at the remaining unvisited nodes and we choose the node that has the lowest distance value. At the moment that value is C, and so node C is marked as the current node. As you can see, C has edges connecting to E and to F. Since we're at node C now, the distance to node E from node A is 25, the distance to node C, plus 45, the distance along the edge to node E. These two values are added together to give a total distance of 70. You can see how the current node C has been put into the previous node field. Similarly, we add 25 to the CF distance of 50 to get a total distance from A to F of 75. And we remember to put the current node into the previous node field. We don't write down the calculation, we simply put the answer into the table. If a calculation leads to a greater value than is already in the table, that value is ignored and the table is not changed. Don't forget to mark the current node as visited once all is done for this pass. Now we look down the table for the next unvisited node with the lowest distance, and it's B, which connects to D and I. B is marked as current, and the distances to D and I are updated. Infinity signs are crossed out, and the previous node field is completed. Now we're building up some momentum. B is now marked as visited, and again we seek the lowest remaining distance, and we can see we will visit node E, marked as current. E connects to G and H. Once again we update our table, this time for nodes G and H. We now have two nodes that share the same lowest distance. We can choose either, and so being logical, we'll choose the node closest to the top of the table. Node D is connected to nodes F and I. This time, something different happens. The new distance from A to I would be A to D, 75, plus D to I, 70, giving a total of 145. This is greater than the existing value of 130, so we ignore this route. The same thing happens with F. The new distance from A to F would be A to D, 75, plus D to F, 10, giving a total of 85. This is greater than the existing value of 75, so we ignore this route too. In this case, the only change to the table will be to mark D as visited. Remember, we're not going to go back from D to B. B is marked as visited and will not be revisited at all. You can see another example of ignoring a visited node here. F is now chosen as the current node, and we will not visit node C as it's already marked as visited. The distance to H, 100, is less than the existing value of 105, so this time we can update the H row in the table. The 105 and E are crossed out and are replaced with the 100 and F just calculated. Moving on, the only calculation to do from G is to the destination node J. This gives us a value of 180, which is entered into the table before G is marked as visited. Now H is the current node. All nodes are visited, and so there are no calculations to be done. Moving on to I, we can calculate that the new distance to J of 160 is less than the existing 180. We need to update our table. We haven't actually finished, as we must still visit J. We visit J, and our calculations are complete. We can now start at J and backtrack to work out the cheapest route from A. We go from J to I, from I to B, and from B to A. So, running back through the graph, our lowest cost route is A, B, I, J. Finally, looking once more at the algorithm, this time it should make a little more sense if you sit down, take some time and read it. Do go through the example again to consolidate your knowledge and to get your own understanding of the algorithm.